Here in this video, we'll look at question 6 on the worksheet, which is another example of how we can use Taylor's remainder theorem to find a bound on the error in approximating a function with the Taylor polynomial. Okay, so here we're looking at the function f of x, which is the natural log of 1/2 x, and the interval in question here, I, is the closed interval from 1.5 to 2.5. Now part A says find the quadratic approximation p2 of x based at a equals 2. Okay, so we'll start out by finding f of 2, which is the natural log of 1, which is 0. Then we need f prime of 2. Now, one thing to simplify the calculation of the derivative, I'm just going to first write f of x as the log of 1/2 plus the log of x, just using the product to sum property of logarithms. And now differentiating, right, this log of 1/2 is a constant, so its derivative is 0. So I'm really just differentiating log of x, which is 1 over x. And so f prime of 2 is 1/2. F double prime, well, just differentiating 1 over x gives us negative 1 over x squared. And so f double prime of 2 is negative 1/4. All right, so then we put that all together and find that p2 of x is f of 2, which is 0, plus f prime of 2, which is 1/2, times x minus 2. And then we're going to have plus f double prime of 2, which is negative 1/4, over 2 factorial times x minus 2 squared. And this simplifies to 1/2 times x minus 2 minus 1/8 times x minus 2 squared. All right, so that is our quadratic approximation to our function here. And now go ahead and look at the graph. So here in blue is the graph of the log function, and we're looking at things centered at this point in black, right, 2 comma f of 2. And now if I graph p2, like we saw in the last video, right, this looks pretty darn good as far as approximating the blue curve. Over here at the endpoints, we can see, yes, there is some gap, and now it's our job in part B to find an upper bound on that gap. Okay, that's what part B says. It says use Taylor's remainder theorem to find a bound on the absolute value of this difference over this interval I from 1.5 to 2.5. All right, so we're going to use Taylor's remainder theorem, which recall says that this difference in absolute value, in other words, the error, can be no larger than this quantity, m over n plus 1 factorial times the absolute value of x minus a raised to the n plus first power, okay? Now, it's really a two-step process, right? We first want to find m, and remember m was a bound on the n plus first derivative of f on this interval I, okay? So here, since we're using p2 of x to approximate our function, n is 2, and so the n plus first derivative is really the third derivative of our function f, and if I differentiate the second derivative, I get 2 over x cubed. And so now what we're asking to find m is how big can the absolute value of 2 over x cubed be on this interval? Okay, and just like we did in the last video, we can look at a graph of the absolute value of 2 over x cubed, right? This is just a decreasing function on this interval, and we see that its maximum occurs when x is 1.5. So I plug in 1.5 in for x into this third derivative, right? And I get 2 over 1.5 cubed. And that is our value for m. Now, 2 over 1.5 cubed can be written in simplified form as 16/27. Okay, so this is our value for m. And then the other step we had to take was in finding a bound on this portion, right? The x minus a in absolute value raised to the n plus first power. Well, here a is 2, and n plus 1 would just be 3. So we're looking to bound quantity x minus 2 in absolute value cubed on this interval, right? As x varies from 1.5 to 2.5. Okay, so how big can x minus 2 be? Well, it's going to be as big as possible when we're as far away from 2 as possible, and that will happen at either one of these endpoints. So, for example, if x is 2.5, then 2.5 minus 2 is 0.5, right? And so we're saying that this expression, x minus 2, is no larger than 0.5 on this interval. And so that expression cubed is no larger than 0.5 cubed, which is an eighth. Okay, so now what we're going to do is put this all together. Okay, Taylor's remainder theorem says that the absolute value of this difference can be no larger than m, which we found here is 16/27, divided by n plus 1 factorial, so that's 3 factorial, times the absolute value of x minus 2 cubed. And now from here we know that this quantity, right, the x minus 2 cubed in absolute value, is no larger than an eighth. Okay, now you simplify this expression and you get 1/81st. And so in conclusion, we find that this difference in absolute value can be no larger than 1/81st on this interval. All right, great. Well, that's going to do it. Thanks so much.